Welcome friends. As the title of the video says, method to solve the group theory problem of the form ... Now, which form am I talking about? Let's see with this example. G is a finite group. Phi is automorphism of G such that phi of x equal to x if and only if x equal to E. To prove that for all G belongs to G, G can be written as x inverse phi of x for some x belongs to G. So you see the form is G is a finite group condition to prove that for all G belongs to G, there exists x belongs to G such that relation between G and x. Before start the solution, please give this problem a try. In this form, I can see the words like for all elements, there exists an element. These words also appear in the definition of surjective function. So we just have to define a function, say psi from G to G, such that psi of x equal to x inverse phi of x. And to prove psi is surjective function. But now the question is how to prove ontoness of psi. That's where this trivial looking powerful theorem comes into the picture. If you want to see why this theorem is true, click the I button here. So now we just have to prove oneness of psi. So let's begin. Let any element x and y in G and consider psi of x equal to psi of y. That is, x inverse phi of x equal to y inverse phi of y. But since x inverse and y inverse are also in G and phi is surjective, x inverse and y inverse have preimages under phi, say x dash and y dash. That is, phi of x dash equal to x inverse and phi of y dash equal to y inverse. So you get phi of x dash x equal to phi of y dash y by the property of homomorphism of phi, which implies x dash x equal to y dash y. Because phi is 1 1, we can write x dash as phi inverse x inverse and y dash as phi inverse. Now separate x and y, we get phi of xy inverse equal to xy inverse. But since we are given that phi of x equal to x if and only if x equal to E, we get xy inverse equal to E, that is x equal to y. Therefore phi is 1 1. And since our domain and codomain are the same, their coordinate are also same. Therefore by our previous theorem, psi is surjective. Hence for any G belongs to G, G can be written as x inverse phi of x for some x belongs to G. I'm not saying this is the method to solve this type of problem, but sometimes it may get lengthy or difficult to prove oneness of the function. So instead, we use direct method, like this example. Let G be a finite group whose order is not divisible by 3. Show that for every G belongs to G, there exists H belongs to G such that G equal to H cube. So clearly the function is x cube, but it may get lengthy to prove the oneness of this function. So instead of this, we use direct method. So for any G in G, we claim that order of G is also not divisible by 3. Because if it is, then since by Lagrange theorem order of G divides order of G, that is group, and this order of group is also divisible by 3, which is contradiction. Therefore, order of element G can be written as 3k plus 1 or 3k minus 1 for some k belongs to integer. See, minus 1 is same as 2 in modulo 3. So if order of G is 3k plus 1, then we get H as G raised to minus k. And if order of G is 3k minus 1, then we get H as G raised to k plus 1. So in this problem, direct method is convenient to use. And there are problems where this method is convenient to use. Like this example. Try to prove this problem by direct method as well as this method. Also try to prove this important problem come theorem. Of course, we just need to prove oneness here or ontoness. And the last exercise question is, in the very first question of this video, add the condition that phi square is identity automorphism of G and then prove that G is abelian. That's it for today guys. Thank you for watching this video. I hope you enjoyed.